integration by parts. This felt like voodoo to me when I first saw it. I was like, you're kidding me. And if you spend a little time playing around with, the product rule differentiating u times v, which is going to give you u prime v plus v prime u. You play around with that a little bit, you can come up with this formula. It's the integration by parts formula. And it really comes from integrating both sides of this and rearranging terms. What happens when you integrate a derivative? Yeah, they cancel each other out. So you're going to get uv. And of course, the properties of the integral say that this is distributive, so you can call that integral of u prime v plus the integral of v prime u. And you can rearrange things a little bit. So I can move this to the other side and get the integral of uv minus the integral of u prime v equals integral of v prime u. So, okay, with a little bit of magic, you can rearrange these formulas and come up with something interesting. Now, this doesn't look like anything much, anything different. Doesn't look like anything useful at all, but it actually does help out. It's as close as you can come to a product rule within the context of integration. Now let me formalize this a little bit more and write it this way. The integral of u times dv, and I guess I should have moved this one over. The integral of u times dv is u times v minus the integral of v du. Now if you want to see me after class, I don't think I'm going to put it on a video, but my Calc 3 or my Calc 2 instructor, when I was taking this, had a colorful way to remember this, but I'm not going to mention that now. In any case, this is the formula that you should kind of keep in mind. Right there. Now, it doesn't look like much. It looks like it just looks just as bad on one side versus the other, but it actually does get some work done. So let's see that as we work our way through these problems. And we'll start with this one. Integral of x times cosine of 6x dx. So, okay. So example A. The integral of x times cosine of 6x dx. Now when you're working at this, what you're really looking at is something like this. So something where you're going to need to identify what's your u and what's your dv. So what's going to happen? Once you make those identifications, then we're going to figure out what the derivative of this is, and then you're going to have to find the antiderivative of this. So in general, if you have a choice in terms of how you set things up, you're going to let your u be something that's easy to differentiate. And this choice is going to be something that's not too bad to integrate. You are going to have to integrate this other thing here. So I'm going to let that be my u, and this is going to be my dv. And by this, I should probably make sure that you realize I'm talking collectively. The whole thing. Cosine of 6x dx. Now, looking at my formula, I need a couple things. I'm going to need the derivative of u, that's going to be my du term, and I need to integrate this to get the v term. So let's start out with the easy part. If u is x, du by dx is 1, or better yet, du equals dx. And that's probably the last time I'm going to show this little middle step here. I'm just going to kind of jump to this. On the other hand, I've got dv equals cosine of 6x dx. I need to find the antiderivative of this. Basically, I'm going to integrate this. Now back in Calc 2, or Calc 1 I should say, what we did was we tried to find, a U substitution and do our U substitution and all that bit. But you're going to do this kind of stuff often enough that I'm going to recommend that we not do the U substitution formally. Let's just do it in our heads. Now let's think about this. Now, when you integrate cosine, the antiderivative of cosine is going to give you your sine term. But then you've got this 6 here. And the way I always think about the 6 is this. If you were to differentiate this, when you differentiate this, the chain rule is going to say you're going to multiply by the derivative of the inside. So you can have the derivative of this times what? Times the derivative of the inside. The derivative of the inside is going to be 6. Integration is the opposite operation of differentiation. So instead of multiplying by 6, when you integrate, you're going to end up dividing by 6. So let's just kind of skirt the problem of that U substitution by dividing by 6. I'm going to multiply that by 1/6. The antiderivative of cosine is what? Sine. Sine of 6x. And that's it. Don't put in the plus constant yet. We'll save that till the very, very end. But don't make your life more miserable by working with that constant. So let's take a look back at our formula. The formula says if I've got this, I can, if I got this, I can rewrite it as u times v minus v du. All right, so let's line those things up. The integral of u times dv equals uv minus the integral of v du. So in our case, that's going to be this one right here. Integral of x cosine 6x dx equals u times v. That's going to be x times 1 over 6 times sine of 6x times 1 over 6 sine of 6x minus the integral of v du. So it's going to be this times this. That's nice. It's going to be this times this. So minus the integral of 1/6 sine of 6x dx. So it still looks like a little bit of a mess, but we did make some progress though. Here we can find the antiderivative of this integral. That's not a big problem. So let's do that. This I'm just going to write as x over 6 sine of 6x minus, and if you want, you can take the 1/6 out in front, integral of sine of 6x dx. And what I want you to do for a second is practice trying to find that antiderivative without doing the U substitution explicitly. So this much stays the same. Sine of 6x minus 1/6. And see if you can't find the antiderivative of this term without actually going through all the gyrations of a U substitution. Now, if you need to do that, go ahead. Don't get this wrong because you're too proud to try and do a U substitution. Get it right, stay in your comfort zone, but you're going to do enough of these things that I don't think you really want to spend the time to write a U substitution for all these things. It just takes too much time. So, Paul, what would be the antiderivative of this, please? Cosine. The 6x is still going to be here. There's a couple other things. Say it. 1 over 6 Anything else? Yeah. Derivative, or the antiderivative of sine is negative cosine, so we have to account for the negative. And then instead of multiplying by 6, we're going to divide by 6. And now that we're all done with our antiderivatives, there's one more thing that's going to be annoying, but I'm going to make sure you guys always remember. What else do I need here? Say it. There we go, plus c. All right, don't forget that constant of integration. That's worth a point. All right, it's only 1 point, but I want you to get those points. Cleaning this up, x over 6 sine of 6x plus 136 cosine of 6x plus c. So, nice. Now, if you're looking at that going, oh my God, then I feel for you, because that's what I thought when I looked at these things for the first time as well. It's not always clear what you're going to let u equal and what you're going to let dv equal. There is a good semi-cure for that. It's practice. Just do a lot of these things. Now, there's going to be some tricks along the way that I'm certainly going to share with you. But for the moment, we'll take a look at this. Are we okay with what we did here? Now, some of this is going to take some time, but you're going to have to identify a u and dv term in your integral, and then go through and say, all right, well, with that u and that dv, then I could figure out a du and a v, and then fill it into the formula. So definitely one thing I would suggest is that you have this thing memorized. Definitely going to need that term memorized. Okay, let's keep going. Example B. The integral of x minus 2 times sine of pi x dx. So this one should start to be a little bit more familiar. A lot of times, a good choice for your u term is some kind of polynomial term, because those are going to be easy to differentiate. And you want something for your dv term that's not too hard to integrate. So both of those are satisfied here. Let me also go a little further. It's nice when your u term will get simpler when you differentiate it, and that's certainly going to be true when you're dealing with polynomials. When you differentiate that, degree decreases, you lose some constants. So that's a good choice for your u term. This is going to be dv. Let me make sure that we include the dx there as part of that. So u is going to be x minus 2. dv is going to be sine of pi x dx. du is just going to be dx. I want you to figure out what v is for this one. That's a good question. I don't know if it takes that size or not. It probably does, but I don't know. Okay. So, Jesse, what did you get for the antiderivative here?
Negative 1 over pi cosine pi x dx.
The dx disappears when you take the antiderivative, so that's a good thing. We'll pick up the dx as needed because when we do v du, that's where the dx will come from. So this du term should always have your dx as part of it. All right, appreciate that. Let's fill this in. I want u times v minus the integral of v du. So u times v, that's going to be x minus 2 times negative 1 over pi cosine of pi x minus the integral of v du. So it's going to be negative 1 over pi cosine of pi x. And here's where we pick up that dx term. Now these two things are going to cancel each other out. So I'll end up with x minus 2 over pi times cosine of pi x. That should be a negative out there as well. Pi x plus 1 over pi times the integral of cosine of pi x dx. So I need to find another antiderivative for that one. I need another sheet here. So negative x minus 2 over pi cosine of pi x plus 1 over pi. Now I need an antiderivative for this. The antiderivative of cosine is what? Sine. So it's going to be sine of pi x. And instead of multiplying by pi, if we were differentiating, you're going to divide by pi or multiply by 1 over pi. Now the one last thing we need is constant. Need that constant of integration. So if I clean this up a little bit, that's going to be a pi squared there. I'm going to leave the negative out in front. Negative x minus 2 over pi. You could factor out a 1 over pi if you wanted to. You're still going to have a 1 over pi here, so I'm not going to bother to do that. 1 over pi squared sine of pi x plus c. Whew. All right. Now, it'd be kind of a pain, but if you're really anxious about this, you're like, I don't know. I don't know if that's right. Theoretically, what could you do to check it? Take the derivative. What should happen if I differentiated this? Yeah, I should get the integrand back here. It'd take a lot of work to show that, but you should be able to double check your work that way. I'll leave that as an exercise for you over the weekend. So have fun. Report back to me. Let's move on down to example C. All right. I think this one had cosine inverse in it. Yeah. So definitely mixing things up here. Cosine inverse of x dx. Wow. This one is like, wait a minute. Now, if you're in my Calc 1 class, I didn't really come down too hard on these things, but let me give you a reminder that the derivative of this, derivative of the inverse cosine, is going to be minus 1 over the square root of 1 minus x squared. If you have the derivative of the inverse sine, sine inverse of x, then it's pretty similar. It's just going to be 1 over the square root of 1 minus x squared. So just kind of a polite reminder on those. And I guess since I'm filling this up with all these arc functions, I'll throw in one more. Derivative of the arc tangent is going to be 1 over 1 plus x squared. So if you need a few of those things, those are kind of the just-in-time things that I like to provide as we're going through things. Some people do a review at the beginning of the semester. I think I like to provide these things right when we need them. Yes?
Like the inverse trig function, the same as like you said, like the arc version?
Yeah, so I could also say d by dx of arc cosine of x, and that would also be negative 1 over the square root of 1 minus x squared. So yeah, these two things are just different notations for the same thing, just like square root of x and x to the 1/2. Just different notations, but you could do arc sine and arc tangent, and they would have the same derivatives here. Okay, so a couple reminders here for us. I'm not going to get obsessive about these things. I'm not going to deal with your hyperbolic functions or your secant, cosecant, arc secant, arc cotangent, arc cosecant. This is enough, but do kind of have these things in mind. I will try and give you a heads up if and when we're going to run into something like that, but for general reasons, just have these memorized if you could. Now, let's look back at this. We need to figure out a u and a dv. So what happens with each of these things? What do we do with the u? Well, we differentiate to get a du. What do we do with the dv? We integrate, antiderivative. Now you got to decide what is what. Now back in Calc 1, I was really adamant about the fact that I wanted you to include this dx. That dx becomes important in these types of problems. Kaiser. Yeah, let's think about it. What would be the problem with putting arc cosine here? Well, we're trying to find its antiderivative. So putting it here means you have to find its antiderivative. That would almost feel circular. We don't know what it is. That's why we're doing this one. So that kind of pushes this one over here. Cosine of x. What does that leave me for my dv term? Dx. So the derivative here is going to be negative 1 over the square root of 1 minus x squared. Here I need the antiderivative. Clyde, what's the antiderivative going to be there?
X.
Just x. Great. All right, so I've got everything I need. Let's put it in our formula. I want u times v minus the integral of v du. So it's going to be the product this way. I'll write it as x cosine inverse of x minus the integral of v du, x times negative 1 over the square root of x. Oh, there's something I forgot here. My dx term. 1 minus x squared dx. You get that dx when you differentiate this and then solve for the differential. Let's clean this up a little bit. You've got a negative here and the negative there. I'll factor that one out in front so I can write it as a plus. And I'll put the x on top. X cosine inverse of x plus the integral of x over the square root of 1 minus x squared. Now my dx. What you're looking for, hopefully, is something here that's easier to integrate than what we started with. And this is what we're looking for. How come this is easier to integrate? Where's my two ladies from this morning? Liz and Gina. I mentioned something about this earlier. What are you looking for, or what's your kind of clue as to what to do when you have something like this? A u sub, but there's a clue as to what to let u equal, right?
Inside the
Inside the square root? Good. Now, what happens when you differentiate a polynomial? What happens to its degree in general terms? When you differentiate a polynomial term, it goes down by 1. And if you look here, you've got an x squared term here, 1 degree less than that, that's an x term here. So that's kind of nudging you towards choosing u equals 1 minus x squared. U equals 1 minus x squared. Du would be minus 2x dx. And looking at what I have in the integrand, I've got an x and a dx term. So I'm going to solve for that. Now some of you might do this a little bit different. That's fine. I'm going to write the minus 1/2 over here, so divide both sides by -2 or multiply by its reciprocal. X dx. I think we're in good shape. So that's going to be x cosine inverse of x plus the integral x dx. That gets replaced by minus 1/2 du over the square root of u. Probably want to clean that one up a little bit. So x cosine inverse of x minus 1/2. What do you think I want to do with that square root of u term in the denominator? How could I rewrite that to make my life a little bit easier? James? Very close. It's in the denominator. Yeah, u to the negative 1/2 du. Nice. So to finish this up, I need the antiderivative here. Add 1 to the exponent. That's going to give me u to the 1/2. Divide by that same exponent. And let's start putting in our constant of integration before we have a chance to forget it. The 2 and the 1/2 cancel each other out. So it's going to be x cosine inverse of x minus just u to the 1/2 or square root of u. What was u taking the place of, though? U was taking the place of 1 minus x squared. So, wow. There you go. There's your final answer. Comments or thoughts on this one? Example C. Okay. I want to get you a fair number of examples because, you know, the one thing that helps out a lot with this is familiarity and practice. Now, Ethan was talking to me earlier about something that he saw on YouTube. Goes by a different name. What did you call it? Yeah, the DI method. So I call it the table method. It might look a little different on your handout because I think I changed things up.
AAA.
It's AAA?
Yeah. Take these electronics.
Okay. All right. Thanks so much. So let's take a look at example D. So the integral of 5z cubed e to the z dz. Integral of 5z cubed e to the z dz. All right. When you have a nice little polynomial here, then there's a little kind of a shortcut thing that you can do. This is what I call the table method. And it's not just me. My calc instructor, when I took calc at OCC, taught me this, and I just thought it was the coolest thing. So we're going to start out by identifying a couple things. We're going to have to identify our u and our dv. Now, what do you want from each of these things? With u, you'd like to see your term get easier when you differentiate it. And with your dv term, hopefully it's not something that gets worse. All right, it's something that you can integrate and not have things get more complicated. So in our case, what's something that I could differentiate and it gets easier? The 5z cubed term right there. So that's going to be my u. How about my dv? Well, that's going to have to be my dv. So let's see, we'll do 5z cubed e to the z dz. Now what happens next? Well, we're going to differentiate these things, right? You're going to get a du term, and you're going to get over here, you're going to integrate. Now I'm not going to worry so much about the dz and the dz term here or here. We're just going to kind of keep on going. If I differentiated this, what would I get? 15z squared. Now, like I said, if you were doing this formally, you'd put a dz here. We're going to kind of do it with this table method. Let's keep going. If I differentiate again, Jameson, help me out. What would I get if I differentiate this with respect to z?
30z.
30z, good. And I can differentiate this a couple more times, right? Yiming, what would I get the next time?
Oh,
If I differentiate this again?
it's
30. And go ahead, one last time. 0. All right, so we've gotten all the way down to as far as we're going to get. Now, how about over here? What do I get when I integrate e to the z? E to the z. And I'll integrate again. Not all at once. E to the z. And 2 more times. E to the z and e to the z. Nice. So the way the table method works, kind of look back, if you look back at our formulas, it's going to be u times v minus v du. So one of the things I'm going to need is that u times v. That's going to come from here. But then I'm going to keep going. And because, you know, sometimes you're subtracting, well, you're always subtracting, that subtraction is going to kind of change some signs a little bit. So let's label these as plus, minus, and minus. And this little downward arrow is really saying multiply these things together. And then add them all up. Now when I say multiply, you're going to include the negative sign where it exists here. So the first term is going to be 5 times z cubed e to the z. And then a minus times this, minus 15 z squared e to the z. And then what? Plus. Keep going.
30 times e to the z.
And then minus 30 e to the z. And what do you think I should finish with?
Plus c.
Ah, well done. I thought I was going to catch you guys snapping on that one. Yeah, plus c. And that's it. You're done. Wow. See, I really need that button right now, man. I'm like missing it. So I will get some AAA batteries for the next class. But yeah, that's it. That's kind of nice. So when it's these table methods, and the table methods are going to work when you've got some kind of a polynomial term here and something that you can integrate pretty easy, like a sine or a cosine or an e to the x term. Those are the types of problems that lend themselves to the table method. So I'm afraid that's it. We're done with that one. We're not done. We're done with that one. Okay. Let's see. What's next here? Let's turn this into a definite integral type problem. If you actually looked at your handouts, you might see kind of a running joke as you go through these problems. I don't know if anyone noticed it or not, but it's there. Let's see, we want the integral. So this is example E. The integral from 0 to 1 of x squared plus 2 e to the negative x dx. So this is a nice one to kind of build on what we just did. One of the big differences, though, is that this is a definite integral. So that we're going to have to pay attention to. But does anyone recognize this function out in front here? What kind of a function is that? Polynomial, right? So if you got a polynomial and some function that you can integrate, then that's starting to suggest a table method. So I'm going to let this be my u, and I'm going to let this be my dv. What are my u and dv terms going to be here? Joseph, what do you got? What do you think we're going to let u equal and dv equal? X squared plus 2, good. And for dv? Yep, e to the negative x dx. Now I'm not going to carry this dx all the way through on either side, but let's work our way down. When I differentiate this, I'm going to get a 2x. When I integrate this, again, back in Calc 1, this was something that we did with a u substitution. But we're not going to do that u substitution here. You're going to have to think about the chain rule, though. Let's think about what would happen if we differentiated this. So, kind of a quick reminder here for yourself. Derivative with respect to x of e to the u, well, it's just e to the u times the derivative of the exponent. So just a kind of a quick reminder there, when you differentiate this, you're going to have to multiply by the derivative of the exponent. What's the derivative of this exponent? Negative 1. That would be if we're differentiating. You would multiply by negative 1. What if you're integrating? Divide by negative 1. But dividing by negative 1 and multiplying by negative 1 are kind of the same thing, right? Doesn't matter which one you do. So I'm just going to write negative e to the negative x. Now if you need to slow it down for yourself and do a u substitution, that's fine. Please do it. But as much as you're going to do these things, I think you're going to want to do these things kind of by thinking it through here. The last one, where we'll stop there. And you do have to, with your choice of u, you have to be able to get to a 0 here at some point. You have to stop. How about the antiderivative here? What am I going to get for the next one? E to the negative x, and then negative e to the negative x. Let's connect these things this way. How's the pattern start out? Plus, minus, plus. So let's be careful with that. Here I'm going to get x squared plus 2 times a negative, times a negative e to the negative x. So I'll put that negative out in front. Let's look at the next one. 2x times a negative times e to the 2x is going to be minus 2x e to the negative x. And finally, 2 times this is going to be a minus 2 e to the negative x. Great question, plus c. There's good news. We don't need to worry about the plus c in this one. Why not? It's a definite integral. Instead, we're going to put between 0 and 1. Now, if you were stuck doing this by hand, I would suggest this. I would clean this up a little bit. You can factor out negative e to the negative x, and it'll leave behind x squared plus 2 minus 2 again between 0 and 1. Let's just double check that. Plus 2, minus 2, minus 2. Now a couple of these things cancel each other out, so you're just left with negative e to the negative x times x squared minus 2 between 0 and 1. Let's put these in. That's going to be negative e to the negative first power times 1 minus 2 minus, and let me bracket it off this way. Minus the lower limit, negative e to the 0 times 0 minus 2. This is going to be a negative 1 times a negative is going to be e to the negative first. Negative times a negative times a negative is still going to be negative. So I'll end up with 1 times 2, which is just going to be minus 2 there. I think I got that right. I'm terribly worried about this minutia here at the end. The big thing to see is that we use the table method, and that at the end, instead of putting in a plus c, we had to go through and do our actual function, our antiderivative, evaluate at the top end and the bottom end. Okay. Let me get you at least set up on one more problem. That's example F. So w squared ln of w between 1 and 2. Integral between 1 and 2, w squared ln of w dw. Now, if you have an easier way to do some of these things, that's great. What you can't do is you can't do a u substitution right away because the w squared, well, that w is in here. It's not something that you get from the chain rule or anything like that. We are going to set up a u substitution, but here it kind of dictates what you've got to choose for which. Now, our u is something that you can differentiate. V has to be something that you can integrate, but it kind of pushes you into one choice. Which one of these can't we integrate, at least directly? And Kaiser might know it, but I'm not sure everyone knows it. There's a formula to integrate ln of w, all right? But that formula actually comes from integration by parts. So, so if you don't know the antiderivative for that, then what is that telling you have to do? Take the derivative. That means you have to make it your u term. And that means our du term, our dv term should be w squared dw. And at least that's something that you can integrate. Du is going to be 1 over x. What's v going to be? What do you get? Or not 1 over x. How about 1 over w? Sorry, 1 over w. And there's actually a dw that you're going to get when you differentiate this as well. Well, what about v? 1/3 w cubed. Nice. If we set it up now, uv minus integral of v du, u times v, all right, that we can do. That's going to be 1/3 w cubed times ln of w minus the integral of v du. So it's going to be 1/3 w cubed times 1 over w dw. Now there's still some limits of integration here, 1 and 2. This is 1 and 2. But what nice thing happens here? Yeah, the doubles cancel, right? So you're just going to have a w squared term which you can integrate. And I'm going to have to leave it here for you to finish up. You're going to find the antiderivative here, and then do your work subtracting the function at the upper limit minus the function at the lower limit. So, whew. All right. Have a great weekend and see